a particular machine learning method rests on a particular choice for a hypothesis space. So there's one choice for the hypothesis space is decision trees, which we will talk today, about today, but we have heard other examples for a hypothesis space. Yes, so some student posted already linear predictors. So another example for a hypothesis space is the set of all linear functions. Okay, so let's start quickly with some example machine learning problem. And the first component is data. Just to remind you, data is understood in a very abstract sense, just as a set, a bunch of data points. And the data point itself can be anything. So it's a highly abstract concept, which makes it very powerful. So you can model almost anything, any object you can model as a data point. However, you must always be clear about how do you characterize a data point? What do you know about a data point and what do you want to know? So what you can measure easily, the properties that you can measure easily about an object are the features. And what you would like to know, the higher level facts or the quantities of interest that are not so easy to obtain about an object is called the label. For example, a data point could represent some movie. And the features, two features could be the duration of the movie in minutes, and another feature, X2, the screen time of a famous Austrian actor, Arnold Schwarzenegger. For those of you which still know him, you might be already too young for this. However, he was quite popular in the late 80s, 90s. And based on these two features, we would like to know the movie rating for the movie. So how good is the movie on a scale from 0 to 10? So this is one data point. And in general, we need many data points. Machine learning only works good mostly if you have a lot of data points. So where do we get a lot of data points? Well, from some movie database. There are big databases of movies which indicate for different movies how much screen time of Arnold Schwarzenegger was there, what was the duration of the movie. And some people or somebody tried to evaluate the quality of a movie. So how do you think we can get the label values, so the rating for movies? How can we get, for some movies, the rating? Yeah, there are platforms, Rotten Tomato, IMDb, or reviews, but who is rating the movies? Who can rate the movie? Humans, yes, but in order to have a good rating, we need experts to evaluate the movie, preferably people which have studied art or studied cinematology, or I don't know if there's such a study. I know there's a study of theater. So not everybody can give a good review. So this is something that experts can do. But we would like to develop a method to predict the rating using machine learning. So we would like to automate the job of movie experts, like the committee members of the Oscar prize. Yeah, so we would like to predict the movie rating, this is the label Y, based on the two features, movie duration and the screen time of Arnold Schwarzenegger. And we consider X1 and X2, these two features, as numeric quantities, as numbers. So we can plot for a few data points, we can do a scatter plot, so we can make a blob or some circle for a certain movie, which is called twins. And this circle is placed at the coordinates, which is given by X1, the movie duration, and X2, this is the screen time of Arnold Schwarzenegger. And then there's another movie, Terminator 1, which had more Schwarzenegger screen time, but was shorter. Then there's another movie, a third movie, The Expendables 3, which had very little screen time of Arnold Schwarzenegger. Maybe it was not good, therefore. Yeah, so we can plot the data points in the feature space. We call this the feature space because in this space, in this plane, the horizontal axis is the first feature and the vertical axis is the second feature. Yeah, and we can also indicate the ratings. Somehow we got the ratings, for example, from some professional reviewers or review platforms. And it's important to remember, like the features, also the labels, what we define as label is up to us. When we design an application or an app, we can define what the label is. Do we want to predict the rating on a scale of 0 to 10? Or do we want to have a binary classification of a movie, which just says, this movie is okay, this movie is not okay. So if the rating is larger than 5, we say the movie is okay, smile. If the movie is small or equal than 5, crying, smiley. So this is then a classification problem. So we have the same data points, but we use a different definition for the label. That's an important point. So the same data points can be used with different labels. So we have turned a regression problem. The problem of predicting a numeric rating is a regression problem into a classification problem where we just want to classify into good or bad movie. So this is just to point out that what I talk about today, decision trees, can be used for regression and classification. So decision trees correspond to a hypothesis space, which allows for discrete labels, like only 2 values in classification problems, or numeric quantities, like in regression problems. Decision trees can be used for both. Yeah, and this is the main part now of our today's lecture, the hypothesis space. In principle, in machine learning, we could use any function as a predictor, any function that takes 2 numbers and outputs a prediction could be possibly used as a predictor. How many of those functions are there? Infinitely many, yes. There are simply too many of those functions. That's why we need to restrict ourselves to a particular class of such predictor functions. And this class is what we call a hypothesis space. And there are different choices for a hypothesis space. One option would be to just consider maps that take a weighted sum of x1 and x2. This is the linear hypothesis space that we have talked about in previous lectures. Today we talk about another class of functions or subset of functions, which is called a decision tree. So there was one question, what if one of the x1, x2 features represents the time? Well, yeah, the feature x1 we consider is the duration of the movie. So this is the time or the duration of a movie. But in principle, you can use anything that you can download easily from a movie database as features. But just for the sake of illustration, I just use 2 numeric features because this allows me to plot data points in a 2-dimensional plane. So I can represent data points easily by locating them, by making some marker at the location given by the features, by the 2 features. Okay, so a decision tree corresponds to a subset of maps. And this subset of maps is constituted by all maps that can be represented by a flow chart or a decision tree. As the name suggests, it's a tree that is constructed by different decisions, smaller or elementary decisions, like, or tests. Is the first feature larger than 100? So is the movie longer than 100 minutes? Yes or no? And in a decision tree, we then follow these elementary decisions or tests along the branches. So let's say this Predator movie is longer than 100 minutes. Okay, then we end up here. And we output y hat equal 8. So we output the predicted label, or the predicted rating is 8. So there was one question, is this decision, these elementary decisions, always binary? So in general, mostly yes, it's binary, but it can be any finite number. So this is called, if we only have two yes or no options, then it's a binary decision tree. But there are also decision trees with more branches. For example, each decision can have 5 different outcomes. So we have then five branches leaving every node. But the simplest case is this binary case. Yeah. So there can be more than 2 branches leaving each node. But in principle, the principle is the same. We represent a map that takes the features as input and then follows some elementary tests along a tree structure and ends in a leaf node. So this is what we call a leaf node. This is a leaf node, and the leaf node defines a certain output value. So this is h of x. So this is one predictor value for a certain type of features, exactly those features which satisfy all tests on the path to this leaf node. So there's a question, if I have like an example with these 2 features, movie length and Arnold Schwarzenegger screen time, and if I know that one feature is relevant, is it better to put that on feature, or should I let the algorithm make it and just give 1 and 2 on and not 1 or 2? Okay, I will try to answer this later. I'm not quite sure if I understand the question now correctly. This tests, but maybe this question points towards how can we come up with these tests. So to some extent, these tests are chosen or tried out. So when you use the decision tree in Python, then this function in Python tries out first the first feature, testing against some threshold. And then depending how well this tree is doing, it might change to some other feature. So it might first test some other feature. But I will talk about this later, at a later point. Okay, so just let us look at the decision tree in the feature space. So a decision tree, again, is nothing but a flowchart representation of a map. So we have, as we come here with the input, the features. So a feature vector, which is given by the 2 features, the movie duration, x1, and the Arnold Schwarzenegger screen time, x2. And then we start following all the tests. We evaluate the tests and follow the branches. And then we end up in some leaf. And a leaf always means a certain output value. And in the feature space, we can observe that each leaf corresponds to a region or a segment of many different feature values. So this leaf here corresponds to this region. Then there is another leaf. This leaf here, for example, is reached by all data points, by all movies whose features are in this region. So a decision tree partitions the feature space into segments like this, blocks, within which the predictor function is constant, is piecewise constant. So for all movies whose features x1 and x2 are such that they end up in this area, the output value, so the function value, h of x, or h of x1 and x2, is 5. Okay. So yeah, one particular decision tree represents a piecewise constant predictor map. And then one important parameter of a decision tree is the tree depth. So how many of these tests do we want to allow in a sequence. So if we only want to do one test, then the tree depth is 1, so it's only 1. If we allow up to 2 tests until we reach a leaf node, then the depth is 2. And in general, this tree depth is the length of a path, or the maximum length it takes to reach a leaf node by following the arrows. So you start here in the root node. So this first test is also called the root, like in biology, the root of a tree. This is the root node. And then we follow the first test, go either left or right. Then we follow, we evaluate another test. So this is a test node. And so on and so forth, until we reach a leaf node like this here. This is a leaf. This is called a leaf node. So far we have talked about single decision trees. And what in Python this decision tree objects represent is not only one decision tree, like here, a particular decision tree with depth 3. And by the way, the depth is what you can define here in this parameter max depth. So if you set it to none, then you don't restrict the depth at all. So the tree can grow as large as possible, or as the memory allows of your computer. So what this object here represents in Python is not a single decision tree, but a whole hypothesis space. Remember, a hypothesis space is a whole set of functions. So in the case of decision trees, the hypothesis space is given by all possible decision trees that involve these elementary tests. For example, compare the first feature with 100 minutes and the second feature with 20 minutes, and follow these tests in this tree structure. Another parameter that we can change is, of course, the value of the output, or the output value for each leaf. So this is a parameter which is tuned, or which is learned based on training data. Okay. So the question now is, how do we find a good decision tree given some data? So we have a hypothesis space given by a large set, typically a very large set of decision trees. If you think about decision trees, let's say we allow maximum depth 10. How many decision trees are there with depth up to 10? It turns out that the number of decision trees scales exponential with the depth. So when you allow depth 10, in principle, you have somewhat like 2 to the power of 10 different decision trees. And this number grows quite fast in the depth. So when you increase the depth of the decision tree. So the question now is, how do we find the best or a good decision tree given some label data? Well, and for this, we need the third component of a machine learning method, which is the loss function. And decision trees can be combined with any loss function you like. So you can use a squared error loss if you have a regression problem, or you can use a 0-1 loss, or what other loss functions did we hear about for classification problems? Yeah, there was one comment, the Huber loss. The Huber loss is used for regression problems, but for classification problems, the logistic loss can be used for binary labels. Yeah, another comment was the Heinz loss. Exactly, the Heinz loss could be used. Yeah, so a decision tree in principle can be combined with any loss function, and you can choose this here. So the choice of loss function is done here in Python. It's called criterion. So for some reason they call it criterion and not loss function. So here they call it Gini. I don't know exactly what that is, but this is also a particular loss function for classification problems. So you can combine a decision tree with almost any or in principle, you can combine it with any loss function, but I'm not sure how many different or what loss functions are supported by this Python objects. Okay. Yeah. So the idea is quite simple. When you have some labeled data, so we have some movies for which we know the features, the movie duration, X1, and the Arnold Schwarzenegger screen time, and we know if it was rated good or not. So these smileys are the ones rated above 5, and the other ones are this crying smileys. And then we have the tests. So we build a decision tree using the tests that either compares the first feature with 100, is it above 100 or not? And another test compares the second feature with 20. And in decision tree learning, we typically have a finite set of elementary tests. So you cannot use any, in principle, you could use any test. So it doesn't need to be just thresholding. It could be some other test or criterion that you can use in these decision trees. In principle, you can use anything that you can program using an if clause in a programming language. So these are sequences of if clauses. You can also think about decision trees as structures of if-else clauses. Okay, so, and how do we then learn a good decision tree? Well, we try to build a decision tree that has all the good or all the data points with the same label, like this one here, all data points with a happy label in the same leaf. So you try to build a decision tree such that all data points which have similar labels end up in the same leaf. And so this should end up in the same leaf, these two, and also these two should end up in the same leaf. But another leaf, of course, because here we want to output something different than here. So this should go into another leaf. Okay. And the question is, how do you find this correct tree structure such that this area is in one leaf and this area corresponds to another leaf? Well, mathematically, it turns out that there's not much you can do other than try out all different decision trees. So you pick, for example, this decision tree, and then look how well does it fit the training data here. And then you try out another decision tree, another element of your hypothesis space, and see how well it fits the training data, and so on and so forth. So the optimization or finding the best predictor map out of the hypothesis space is in general a combinatorial problem. So you have to search over a large set of different decision trees. And this is a non-convex and a non-smooth optimization problem. So you cannot use, for example, gradient descent, which we can use for logistic regression or for linear regression. So this learning a decision tree is typically a computationally challenging problem. Okay, so that's basically the theory behind decision tree, or the most important theoretic aspects. A decision tree is nothing but a flow chart of a predictor map, and by considering a set of different decision trees, for example, all decision trees of depth at most 10, we have a set or a space of different predictor maps. This is a hypothesis space. And we can then pick a good predictor map out of this hypothesis space by using any loss function. So decision trees can be combined with any loss function of your choice. So decision tree corresponds to a hypothesis space, but it doesn't tell anything about what loss functions you use. In particular, decision trees can be used both for regression and for classification problems. Yeah, so that's my lecture part. Are there any questions at this point? I would have a short demo. So is Yoni here?
Yes. Yes, so can you please share your screen?
Yeah, you need to first stop your screen sharing. Thanks. Easy to screen one. There?
Yes.
Great.
So here you see a particular data set. This is what is this? Is this a classification or regression problem? Are there any ideas? So we see a scatter plot in the feature space. So we have two features, two numeric features, and each element here that you see is one data point. So this is a classification problem because we have two types of data points. We have one type is crosses. So this is one class of data points, which might be cat images. And then we have another type, which are circles, which might be dog images. But I don't know. Do you know the meaning of those labels here, or is it just synthetic data?
I actually forgot what they...
Is it pedestrian crossing or not?
Yeah, I think it was pedestrian crossing or... Yeah.
Okay, but nevertheless, it doesn't really matter. So we have a bunch of data points, which we use as training data because we know the labels. So we fit a decision tree using the Python object decision tree classifier with a max depth of 20. And yeah, could you highlight the definition of decision tree classifier? Yes. Here, this line defines an object ZLF, and this object represents the whole hypothesis space. So the CLF doesn't represent a particular decision tree, but a whole set of decision tree which has a depth not more than 20. And then we tell this object, find the one which best fits the data. So we call this fit function, and then we see what we got. So everything that is shaded, is it red, orange, is predicted by being in the same class as all the circles. And everything that is in the region that is shaded blue is predicted in the same class as the crosses. And it seems that it's perfectly classifying the training data. Yes, the accuracy is 100%. So we got a decision tree which in some sense perfectly fits the training data. So first question, when we compare this with a linear classifier, could we achieve 100% accuracy with a linear classifier here, like logistic regression? Yeah, very good comment. No, why not? Because a linear classifier looks always the same in the feature space. A linear classifier partitions the feature space into two half spaces, and from this interwinding data points here, I see you cannot find a linear line that perfectly separates the crosses and the circles into two half spaces. So it's not possible to find a linear classifier with 100% accuracy, but we found a decision tree with 100% accuracy on the training set. So can we now conclude that decision trees are better than a linear classifier? No. Okay. Why not? Yeah, there are some comments which mentioned overfitting, and it depends on the problem, depends on the data. Very good. So from what we see here, the decision tree is a better fit to the training data. Yeah, disregarding computational time. So it might have taken longer to execute this CLF.fit function compared to logistic regression.fit. But putting aside computational expensiveness, the decision tree makes a perfect fit to the training data. So why could this be not good in reality? Or why is our intuition telling us that this is not really good?
Can I answer here?
Yes.
The problem is that if we get a circle, a new data, a circle that is, for instance, here.
Yeah.
It would be a circle, obviously, but the decision tree would treat it as a cross because it's in the blue area.
Yeah. But why should we get a circle there?
Because everything points to it being a circle, since these are most likely just outliers from the crosses.
Yeah. So it seems that the data, the intrinsic structure of the data doesn't really correspond to this somewhat crazy decision boundaries of the decision tree. And one idea could be, or one argument could be, if we disturb the data points a bit. So if we move any circle or any cross a bit left, right, up, down, then it should not have too much effect on the classification result. However, if you look, there's an island, this horizontal island, very thin horizontal, or this here, yeah, a bit above this. Yes, this one. If you move the circle here a bit, you end up in another classification result. So it's not robust in the sense, if the data is a bit perturbed, it makes an error. And we will see in round 4 that this robustness is related to problems like overfitting. So it's overly fitting the training data, and it's not really finding the intrinsic structure that we would consider natural. And one such natural structure is that the prediction results should be constant or should not change too much if we move data points a bit. And here we have this very thin island of this orange, yeah. And this is highly unstable. If we move one of these two circles in this island a bit, they're in the wrong classification result. And we don't want such predictors. We want predictors that do not change too much if the features are a bit different, are a bit perturbed. And this robustness can be ensured by using techniques called regularization. So we will hear in round 4 about regularization techniques, and combining decision trees with regularization techniques yields very powerful methods. These decision trees in combination with regularization techniques, which is then called random forest classifiers, they are often competitive with deep neural networks. So I know some applications where these random forests, which are based on decision trees, are better than deep neural networks. Okay, so there are some questions. Yeah, so there are some comments. What if we use only 80% of the data and then 20% to test, so to test then on the other 20%? Yeah, so this is called validation, and this is one technique to test or to diagnose if a predictor is robust. And we will look in this in more detail in round 4. Yes. So another comment, why is it saying it's 100% accurate when we have outliers? Well, outliers are a subjective notion. All we can do is count how many data points are falling, or how many circles are in the blue area, which are wrong classifications. And there's no single circle which falls into a blue area. So it's perfectly classifying the training data. And the decision tree, the program is stupid. It doesn't know what an outlier is. So you need to tell, or you need to have an idea what could be an outlier from your own experience. But the decision tree classifier per se, he doesn't know anything, or she doesn't know anything about outliers. So then another question, how it performs with more than 2 features. So this basic behavior is the same, no matter how many features. The advantage of using 2 features is that we can illustrate it nicely on a 2-dimensional plane. Yeah, so another comment, so there should be space around the crosses and the circles, exactly. So one way to regularize a decision tree classifier is to only learn decision trees which have some backup areas, some buffer areas around each circle. For example, in this thin in this thin red island here, yeah, this has no buffer in the vertical direction. So in order to make this robust, we could say we only want to learn a decision tree which has some buffer area here. Yes, so this is one way to do regularization. Okay, any other comments? Yeah, one question, what is the loss function in this case? Yeah, I think this is the default loss function because you didn't specify it when you define CLF with the decision tree classifier object.
Yeah, it's the default.
I guess it's the Genie, it's called Genie, but you have to look it up in the Python documentation. Okay, any other questions? Yeah, one comment, is the depth of the decision tree a hyperparameter? Yes, exactly. That's what we call a hyperparameter, the depth. Yeah, could you please try out a depth 2? Make it smaller. So we only allow very simple decision trees. So we get simpler regions. We get only two regions here. So the accuracy is clearly not 100% anymore, but does it look better or worse intuitively? The new classifier. Better, yes. It somewhat looks better, makes more sense. And this is strange because the accuracy, so the hard facts, the numbers, the accuracy is smaller, but it looks better. And this discrepancy, we will see how we can use cross-validation or regularization to make this discrepancy between training error and the general or the generalization performance. So how well will the classifier do on new data? This is something we can handle using cross-validation or regularization techniques. And this we will see in round 4. Most likely we will release round 4 next week. Okay, very good. Any other questions? One comment, I worked with time series data. Where time series fall within machine learning problems? Time series data corresponds to a particular choice of data points. So in time series data, one data point corresponds to one time point. So this gives the data some structure, like a time ordering, but this is beyond the scope of this course. There are special courses on time series data. Then another comment, can a third feature be used for validation? I don't see how this works in general. In general, we use the same number of features for training and for validation. So we do not change the number of features between training and validation or robustness methods, regularization methods. Okay, so thanks a lot, Joni. We will put the record. Are you okay with putting this recording also on YouTube?
Yeah, sure.
Yes, thanks a lot. So you get the recording, a link to the recording soon, and you can ask further questions on Slack or by email. Thanks a lot and have a nice evening. Bye.